As to substantive matters, let's see. I guess I regret the grotesque, incoherent catastrophe that occurred this morning. It seems to me that, as far as I can tell from the looks on everybody's faces and from the questions that were being raised and so on and so forth, we didn't even begin to get to anything useful to anybody here until we started near the very end a more detailed discussion of some specific attempts to solve the measurement problem. So I'm sorry, I didn't really know where to start, although looking back on it now, it's not easy to imagine what audience what I said this morning might have been appropriate for. But it clearly wasn't this one. So I take it, what I ought to do is throw the plan out the window. There are a couple, there are a bunch of issues, I want to talk a little bit more about GRW. I want to talk a little about Bohm. I want to talk very little about many worlds, because David is going to do that in more detail tomorrow. And I think there are probably some things worth talking about in connection with non-locality. So that's what I'll do, but people should do a better job of driving me with interruptions and questions and comments and addenda and so on and so forth. Okay, so I think we left off talking about the fact and the consequences of the fact that we were going to shift to a Gaussian. Because otherwise the violations of conservation of energy and GRW associated with each of the hits would be potentially, or more than potentially, with probability 1, infinite. Good. There's a lot to say in connection with that. A problem that immediately gets raised here is the so-called tails problem. That is, the minute you shift from the delta function to a Gaussian, or from a function with compact support to a function that doesn't have compact support, the following worry arises. Look, especially on the standard way of thinking about what it means to be in a superposition. A question arises like, I don't understand. Suppose I have a superposition of a macroscopic object being over here and being over here, and the macroscopic object quickly gets hit by one of these GRW Gaussians. The reason it's quick is because the macroscopic object contains many, many, many degrees of freedom, so that even though the collapse rate per degree of freedom is low, n times that collapse rate, where n is the number of degrees of freedom involved with the macroscopic object, is very, very high. So a collapse is likely to occur quickly. So very quickly, you're going to get a multiplication of the wave function of this thing by a Gaussian centered, say, either here or here. Let's say it's centered here. The worry is something like this. Look, either it's the case that the state of the world is a superposition of the object being here and the object being here, or it's not. Okay. It is, that is, either there is a fact of the matter about whether the object is here or it's here, or there's not a fact of the matter about whether the object is here or it's here. What we're told to think by the eigenstate eigenvalue link or whatever physicists use in its place, the circumstances under which there is a fact of the matter about whether the object is here or here is if the wave function doesn't have support that extends across both of these regions. Okay? But the Gaussian does have support which extends across both of these regions. The amplitude of the wave function is much, much lower here than it is here. Okay? But it's not zero. Okay? David Wallace has pointed out that if you actually use a Gaussian, the fact of constant exponential decrease out here, okay, there's a certain sense in which this looks like it's going down very smoothly out here. There's another sense in which it's going down very violently, okay. The ratio of its total value to the amount that it goes down is huge, okay. So that really, this thing, out here in the tails, objects would get distorted by this tail. But I don't see why it's not just as amenable to GRW to have something that acts like a Gaussian until it gets very low and then just stays flat for 1,000 miles or something like that. And in that case, that kind of an effect isn't going to be there. So there's a worry that people usually refer to as the tails problem. The content of the worry is either you get rid of the superposition altogether or you've done no good at all. Okay? There's a countervailing intuition, a vague intuition of the form, come on, how could that be? I mean, in a quantitative sense, we're getting really close to what we thought we wanted here. How could that be doing no good at all? Yeah?
So I kind of assume that the reason you want to use a Gaussian is that Fourier transform of Gaussian to Gaussian. So it'd be Gaussian in both momentum and position space.
Oh, no. But as somebody pointed out, momentum and position space aren't at all on a footing here. Okay? The basic strategy of a theory like GRW, and this applies to Bohm as well, okay, is that what you want to do to solve the measurement problem, okay, is to make sure the material objects are in determinate spatial positions, okay, spatial positions, okay. There was, there's a backstory you could tell to this. All of this craziness about momentum and position being on the same footing. Okay. This is, at least in a deep metaphysical sense, of course, there is a sense in Hamiltonian mechanics where they're mathematically on similar footing. But there's a deep intuition that, say, Newtonian mechanics was about positions. Okay. Momentum is something you invoke in order to help you keep track of how the positions are changing with time. Okay? But the positions have very much a special status. Positions have very much a special status in the GRW's theory. Positions have very much a special status in Bohm's theory. Once again, the thought is what we need, and one of the things we need to do in order to design a solution to the measurement problem is be a little bit more concrete about what the problem is, okay? The original version of the problem is measurements don't have determinate outcomes. There's not enough there to sink your teeth into by way of designing a physical theory to solve that problem. That is, to make it a requirement of your theory that measurements have outcomes is just too abstract to give you much guidance. Okay? So there's a standard sort of, there's an idea of what it would mean to make measurements have outcomes that's implicit both in Bohm's theory and in GRW. And that is an idea like what would suffice, something that would suffice to make sure that measurements have determinate outcomes is to make sure that at least macroscopic material objects always or almost always have determinate spatial positions. So there's definitely, these theories are definitely not respecting the sort of mathematical symmetry between position and momentum that's inherent in GRW. And defenders of them, I would think rightly, would say there's no good reason for them to respect them. Shelley, do you want to say something?
Yeah, you're raising the tails problem. Suggests another question about exactly what GRW says and how it's different from orthodox quantum mechanics.
Mhm.
I mean, the most famous way in which it's different is the way you described. You change the Schrodinger. But how much of the rest of what you described, for example, that the observables correspond to self-adjoint operators, the eigenvalue, eigenvector league, how much of that
Good.
is retained?
Good.
About this, there's definitely a lot of disagreement.
Right. Right. I mean, let's say a little bit more about that. I think, David, I'm sorry.
No, well, it's kind of linked, but okay, yeah, let me just say this fairly quick. I mean, just that you set this up as it's the eigenvector eigenvalue creating a problem for GAW because it tells us it's small, but it's worth flagging that it's a theorem of non-relativistic quantum mechanics that no quantum state has exactly zero in the open set for more than an instant. So there's a sense in which this
isn't their fault.
Yeah,
right?
and I mean,
That's right. No, it's absolutely.
Yeah.
I mean, this is just what I wanted to expand on.
Yeah.
I mean, thank you for raising this. Right. It seems to me when this problem was raised, I think it was well. From what I remember, GRW responded absolutely rightly with some kind of initial reaction like, "Excuse me, this is not our fault, okay? This is not specific to this theory." This raises a question which it's kind of scandalous wasn't raised before, of exactly what we think we mean when we speak of quantum states representing physical situations, okay? And when we imagine that we know what kinds of quantum states are going to represent familiar physical situations like the chair being here or something like that. Because as David just said, it's a straightforward theorem, okay, of non-relativistic quantum mechanics. That a wave function can't have compact support for more than an instant, okay? A wave function that has compact support, a wave function that goes exactly to zero outside of any region at one instant, the next instant is going to grow tails, essentially because it's a feature of any wave function with compact support that it has momentum components in it that go up to infinity. Okay, so it's immediately going to spread out. Okay, so whether you were thinking of collapse along the lines of von Neumann or Wigner, or no matter what you were thinking of, how was it ever going to be the case that that you ever got yourself wave functions for more than a single instant that corresponded in accord with the eigenstate eigenvalue link to there being a determinate matter of fact about whether this chair was here or on the moon? Okay. So yes, this raised a much deeper problem in the, vis-a-vis, and a much more general problem about exactly how it is that we think that things like wave functions represent physical states of the world. And there's a great deal to say about this. That is, it seems to me that you could rightly see all of the various positions about primitive ontology, all kinds of stuff like that, as flowing out of a question that starts with this tails problem. I don't know if you think that's a reasonable way to look at it or
That's
not.
fine.
Yeah.
I mean, I don't think that I wouldn't be really the motivation, but it is a motivation.
Right. Yeah.
So to solve the tails problem, GRW is this sort of flat cutoff so that it introduces the next.
But that won't work. No, that won't work.
Well, it introduces an extra free parameter, but you're saying that.
Wait, maybe I didn't even understand your question. I'm sorry. I should have let you finish your sentence. To solve the tails problem, GRW do what?
Cuts off the Gaussian and makes it flat.
No, that doesn't solve it.
You're explaining this a moment ago why it doesn't solve it.
Right.
Okay, but what I was trying to say is that if you try to solve it that way, you're introducing another free parameter.
No, but I don't even know why you. That doesn't even look like it's going to solve it. Indeed, I introduced that. As a way of hanging on to the problem. That is, as a way of sort of getting around what seemed to me not a sufficiently general solution to the problem that might have come out of remarks like David Wallace made about what the actual Gaussian entails.
My solution would be pretty bad in the car road.
Right.
My quote solution is that all people in the tails die of radiation.
That's right. It's very unpleasant. Right. That's right. Right.
I was wondering how many more free parameters you need to add, but maybe that's not the...
No. But that isn't an attempt to solve the tails problem. That was an attempt on my part to make the tails problem clearer and more vivid in light of the things that David pointed out. There's a real issue there. Maybe we want to come back and discuss these. That is. So this makes vivid a certain sort of question, which wasn't as vivid before this problem started to be discussed, I take it. A question about exactly what the relationship is between the wave function and what it's correct to say about the physical situation of the world. One of the things that emerges from this, and this I take it is what Shelley is saying, is that whatever that relationship is, it's probably not well captured by something like the eigenstate eigenvalue link.
Does anybody think it is?
I don't know.
Do you?
Do I know? I don't.
Probably very. I mean, I don't know anybody working in GRW who actually
No,
thinks.
I don't.
In this position case, the way part of why I'm accepted about the eigenvector eigenvalue link being a good representation of how physicists conceptualize.
Say it one more
It's
time.
kind of fact that the eigenvalue link gets positioned so wildly wrong is part of why I'm a bit nervous about it being the right way to read physics literature.
But what do you mean it gets positions? Look, let me put it this way, actually. If I had to pick, good, so maybe a useful thing to do is to start a little debate, okay? If I had to pick one person who it seems to me is writing nowadays as if the eigenstate eigenvalue link is the right way to think about it, it's you and Harvey Brown, okay? That is, there's a paper by the two of you, okay, where you say, look, this is supposed to be an argument for many worlds, okay? Where you say, look, everybody in the discussion agrees, okay, that if we get, a billiard ball wave function with compact support, that's a billiard ball.
That compact support for us, I think. Gaussian's fine.
Well, but then what did you mean? That is the deal. I don't know what you mean by that. You wanted something to be true, such that if you had two of them, you had two billiard balls.
Yeah. Well, the claim was, I'm not pleased to defend it here, because I think it's the eternal thing we haven't talked about. But
Right.
The claim was that we know, just something that we know in quantum mechanics, in the practice of quantum mechanics, let alone metaphysics, we know what kind of things are supposed to represent singly localized systems on classical trajectories. And the claim was, I don't essentially want to defend here, but the claim was that if our theory delivered things just of that kind,
Right.
if, say, Schrodinger's intuition was originally right, that you could write the theory in terms of wave packets that remained localized and didn't spread out, then we wouldn't be worried.
Well, maybe we should save some of this discussion for later if we get into. All right, we'll save it for later. There was a hand up. Yeah.
I was just going to say that if you asked me for a quantum state for that chair as like a rough guess, I'd use a coherent state.
But why is that? That is, what's exactly the technique in the back of your head when you're saying that? For reading off the physical situation of the world from the wave function.
That's the best I can do to give it a definite position and momentum.
You're not really asking.
No, but I don't. If that's the best you can do in the theory that's fundamentally true, does that mean? I don't understand what that means. If the wave function of the chair has a certain finite value out here, what's the right thing to say about whether or not the chair is there? It's unlike, you mean, but it either is or it isn't?
I'm not trying to outline an interpretation of quantum mechanics. I'm just saying, if you ask me to assign a quantum state to that chair,
And I'm not allowed to ask you why?
I just gave you a reason why.
No, you didn't give me a reason why. Is there something else I want to know? What's the right thing to say about whether or not the chair is there?
It's a silly thing to say that the chair is there.
You mean so it's false that the chair is there?
It's silly to say.
I know, but I don't want. I want sort of factual claims, not claims, not meta claims about the statement.
Shut up and calculate.
The exact sense in which it's silly depends on your interpretation. But
Give me one.
There's a probability that it's there.
No, oh, that means it's either there or it's not. I think most people don't. That means there's a fact of the matter about whether it's there. He didn't want to say that.
Yeah, just as a kind of shape of the debate before, I mean, look, there are kind of two problems. It claims that there are two problems which are kind of quite the same problem,
Right.
but which perhaps have the same solution or overlap and relate to one or the other. So I think the problem that says, okay, our theory seems to be delivering these quantum states where even if they use a given quantum state to represent a system that's totally macroscopic definite, I can't hold on to macroscopic definiteness because of superposition, because of measurement, all that kind of stuff.
Right.
There's then another problem which isn't quite the same problem, which says even those quantum states that are normally used in physics to represent things that are said by the representatives who macroscopically definite, it's not kind of unclear how to do the metaphysics of those states.
Highlight. It sounded the same to me. Pinpoint. Focus on. Highlight the difference.
Yeah, suppose we lived in a world. The dynamics could be like. Suppose we lived in a world where there were a whole bunch of wave packets. They stayed localized, they stayed Gaussian style,
Right.
They bounced off each other in various ways,
Right.
traced out the trajectories of things that were fairly particular.
Right.
There might well still be a metaphysical question about how to understand that world and relate it to an apparent world of precisely localized points, but the problem wouldn't be quite the same as the
Well,
original.
yes, I mean, good. That gets to. I take it with your appeal to talk about them bouncing off one another and so on and so forth. The way you tell when and where there are billiard balls is by some kind of functional criteria. Okay. That sounds like the basis of the metaphysical view too. It seems to me that's the right way to do it.
There might well be a metaphysical view one could get at quite quickly. I'm just saying that the problem itself had a different shape. It wouldn't be the kind of the same sort of screaming paradox of the cat and the cat's life at the same time.
Okay. All right. Anyway, let me highlight this and go on for the moment, and maybe we'll come back to it. So there is a puzzle on GRW. By the way, something I don't remember explicitly saying this morning, but I take it from the discussion, it's obvious to everybody. Because in a superposition of, say, a macroscopic object being here and a macroscopic object being there, what I have is an entanglement, is a state which is entangled between all of the microscopic constituents of this macroscopic object. So that is, this is a state in which particle 1 is here, and particle 2 is here, and particle 3 is here, and particle 4 is here, superposed with a state in which particle 1 is here, and particle 2 is here, and particle 3 is here, and particle 4 is here. Because of that entanglement, just one of these particles getting hit by one of these GRW collapses is going to snap the entire macroscopic object, okay, into either something, a wave function of its center of mass is either strongly peaked here or strongly peaked there. That's sort of the genius of the GRW idea, okay? They've got this perturbation of the normal dynamics, which has almost no effect whatsoever because of its rarity, because of the width of the Gaussian, and so on and so forth, on individual, well-isolated microscopic systems. But if you have a macroscopic object in a superposition of being there and there, because of the entanglement that kind of superposition entails among the microscopic degrees of freedom of an object like that, just one of those degrees of freedom getting hit by one of these collapses is going to have the effect of collapsing the wave function of the entire macroscopic object onto being either here or there, and doing so, moreover, in a very short amount of time. Okay? Good. That's how the GRW theory works. The GRW theory, on the other hand, through the tails problem, raises a question, you know, that once again people should have noticed a long time before the GRW theory, but clearly weren't taking their collapse theory seriously enough to notice, about exactly what the relationship is between the wave function and the sort of fundamental ontologically correct situation of the world. Okay? And this is a topic about which there's been a great deal of debate over the last 6 or 7 years. A lot of people, there are people who take it that that raising these kinds of questions seriously requires us positing some other object besides the wave function in a theory like GRW, some object that's located in three-dimensional space rather than in a three-n-dimensional configuration space in which the wave function undulates, some kind of mass density floating around in three-dimensional space, or various other things, all of which supervene on the history of the wave function, can be read off of the history of the wave function, but are regarded as ontologically distinct from the wave function. Other people have tried to make sense of their so-called wave function monists, have tried to make sense of there being only the wave function. The fact of our really trying to write down a scientifically serious collapse theory, like we do in GRW, is one of the things that has prompted a lot of hard thinking and vigorous discussion of exactly what the ontology of quantum mechanics is. Okay? Good. Let's talk a little bit about Bohmian mechanics.
Can I ask you a question about
Yeah.
GRW?
Yeah.
I mean, the way you described there's a superposition, and then there's a GRW hit, and it essentially collapses either here or there.
But there's a lot in that word essentially, but yes, go ahead. Yeah.
But when it's in the superposition, is it just potentially here or there?
No, well, it depends on your, so look, what Shelley said I think is correct, okay? The one thing that's surely out the window, once you start thinking about this stuff hard, is the eigenstate-eigenvalue link and this old-fashioned way of talking about superpositions and so on and so forth. There are several attitudes you could adopt towards this. Attitude one. The way to think about a theory like this is to think of the actual fundamental physical stuff of the world as consisting of the wave function itself. Okay? Don't think of the wave function as some kind of description, abstract description of the world, or a compendium of probabilities, or something like that. It's the stuff. It's this goop. It's this field, okay, floating around in this very high-dimensional space. Okay? And it is somehow the undulations of this field itself. It's the undulations of this goop itself, okay, that are the history of the world. And this goop being in a certain particular shape corresponds to there being a chair over here and this number of people in this room and so on and so forth. And this goop having a different particular shape corresponds to the chair being in a different position and a different set of people in the room sitting in different chairs and so on and so forth. Good. There are people who say, gee, that doesn't make sense. That doesn't make the kind of contact I want my fundamental ontology to make. And I think Shelley's going to talk, you're going to talk some about this tomorrow, yes?
I don't think I'm going to talk about it in connection with GRW.
I see, okay. There are people, I mean, we can have a similar discussion in the context of Bohmian mechanics. chance and will. But sticking for the moment with the context of GRW, there are people like Shelley and Tim.
Giancarlo,
Giancarlo,
G himself.
G himself. Who say, G, who say, I just can't get my head around that. I don't understand, a physics that's a really adequate account of our experience. I mean, I want to describe this sympathetically. So correct me where it's appropriate. A physics that's going to amount to a genuinely explanatorily successful account of our experience has to, at some fundamental level, have stuff that's floating around in ordinary three-dimensional space. Okay? And it has to be there at a level that's fundamental rather than emergent in some sense. That is, in this wave function monist attitude, you're going to try to tell a story about how the undulations of this three-dimensional goop effectively give rise to an emergent three-dimensional space with emergent material objects floating around it. Okay. There are people who say, well, you should say it. Either, the objection may be, or maybe a combination of these objections. The objection may be, I don't see how this emergence works. Or even if the emergence does work in some formal sense, all this is going to do is going to establish some kind of formal mapping between the stuff going on in this high-dimensional space and what's really going on in the physical world, which is in three-dimensional space. But having that kind of a mapping isn't genuinely enough. There needs to be genuinely something fundamental floating around in the three-dimensional space. So that what people like this do in the context of GRW is explicitly add to the ontology, okay? They say there's a fundamental three-dimensional space. There is, on one version of this ontology, something they call a mass density floating around in that space. The way you calculate the value of that mass density at any particular point in the three-dimensional space is from the wave function at that time, basically using the Bohm rule, okay? Basically using the expectation value of the amount of mass that you would find at that point in the three-dimensional space, calculating from the wave function. So you've got a fundamental object floating around in three-dimensional space, rather than, as the monist would have it, an object that effectively emerges and isn't explicitly added from the undulations of the wave function. Yeah?
So you keep throwing around this word fundamental, like you have some direct access to space, that you know the space is fundamental.
Well, I'm expressing somebody else's opinion here. Or I'm maybe inadequately expressing somebody else's opinion. Yes, I think, I think the right way to decide what's fundamental is to see how your best physical theory ends up, okay? The best scientific account you have of your experience ends up. That'll identify, that physical theory will identify certain parts of it as fundamental and certain other parts of it as emergent. I think there is another view that says the theory is just a non-starter for me. I don't understand how the theory is even a candidate for an explainer of our experience unless it has a three-dimensional space in a certain way built directly into its foundations. Okay? Now, this is not going to amount to an objection to something like string theory, say, which has, 11 dimensions or some higher number of dimensions. Because in that case, the three-dimensional space is a subspace, is a straightforward subspace of the 11-dimensional space. Nothing like that is going on in this space here. Okay. This space is much more remote from the three-dimensional space of our everyday experience than, say, the 11-dimensional space or 27-dimensional space or whatever it is, or string theory is. But I take it the way you decide what's fundamental is you get the best scientific account you can of your experience, and then you let that scientific account tell you what's fundamental.
Probably the stuff that's fundamental.
What's that?
The stuff that's fundamental is going to be just the stuff which we don't have access to because it's on the deepest level.
Right. That's right. So yeah, I take it you agree with that last statement. Yeah, the way you decide what's fundamental, the way your experience feeds into deciding what's fundamental is just to the extent, which is of course a tremendous extent, to which your experience constrains what ends up counting as the best scientific account of your experience. But it's then, once that account is in place, I take it it's from that you learn what's fundamental.
But then you shouldn't have any bias that space is outside. That's actually
So I didn't present Shelley's view sympathetically enough. I don't. You should say more.
You're going to have some bias, and there's going to be disagreement about what's necessary, what it's necessary to have in a theory as fundamental and what isn't. But for me, it's important to have something like a 3 or 4 dimensional space or a 10-dimensional space which is related to the 3-dimensional space in the usual various kinds of ways, pedestrian ways, let me say, even though they're not so pedestrian really. But that's what David was referring to before.
Right.
And you have stuff in the space.
But Shelley, he's asking, let me press his question on you. Because you said a minute ago that you were agreeing with me that the way at the end of the day to decide what's fundamental is to look for the best scientific account of our experience and then let that teach you what's fundamental. And it's only through that procedure that we ultimately get access to what's fundamental. And indeed, you said that fundamental stuff is going to be in a certain way remote from our experience.
Absolutely.
But he seems to be saying that the prejudice you're owning as your own in the last statement you made is pulling in a different direction.
I mean, I think the crucial thing is what will count for me as an adequate explanation of my experience. It's hard for me to see how that's going to really work in a coherent way unless I have stuff in space-time. I just have never seen it. I've seen lots of attempts in that direction, but they leave me cold.
Shelley, let me consider the following fairy tale. A guy says, I'm a big fan of statistical mechanics. Think about classical statistical mechanics. I think it's right. This may be more addressed to the way Tim defends this than you do, so maybe the right answer is this is just orthogonal to you. But tell me. Guy says, I like statistical mechanics. I'm perfectly willing to believe that objects like gases, which look continuous sort of on the macro level, really aren't. They're made of many discrete subcomponents. I'm willing to believe that pressure, that what looks like a continuous pushing of the gas on the wall is really the sum of a lot of smaller, discrete impacts, so on and so forth. I'm willing to believe all of that. But I get off the train when you start talking about heat, okay, or temperature. I can understand how to see pressure in discrete impacts just by a kind of coarse graining or squinting or stepping back or something like that. But the guy says heat is a completely different story, okay? my idea of what it is to be hot just doesn't have any conceptual relationship at all with motion of particles. It's just apples and oranges. There's no connection to it, okay? I'm perfectly willing to believe that there's a law to the effect that temperature is determined by motions of particles, okay, by average kinetic energies and stuff like that. But you want to really tell me heat just is motions of particles? It's crazy talk. They have nothing to do with one another. There's no conceptual relationship there at all, okay? If you want this theory to really make sense, to really explain our experience, you need to add another ontological component to the theory. Let's call it caloric. People used to call it that, okay? I'll give you a formula for the density of caloric in space as a function of the average kinetic energy of the particles in that region of space, so on and so forth, okay? We've got a perfectly good theory here. Why am I insisting on adding this, even though it supervenes completely on the situations of the particles? Just because without that it's a non-starter. Okay? You want to tell me that heat is correlated as a matter of law with those motions? That's fine. You want to tell me that heat is those motions? It just don't make any sense to me. There's no connection. Suppose somebody were to say, that's what the mass density theory sounds like to me.
Yeah.
What would the appropriate reaction be?
First, I'd be happy if a student said that, because that would mean, while he has a lot to learn, he's at least really wants to understand, which is so rare.
Good.
So the second thing, so I would have, at first a lot of sympathy, and then I'm sure, and you're sure, that after a few hours of discussion, progress would be made. And of course, your question is, so what's the difference in the cases?
Right.
Of course, in this particular case with the heat, what plays a big role in the thinking of the student or whoever it is you're talking about is the distinction between, is the sensation of heat. And the talk of heat is so connected to talk of the sensation of heat. And if you just don't see the sensation of heat in that molecular ocean, you're not going to be happy.
Right.
So there's going to be some work to be done in tying that apart. Of course, you just have to go back to Galileo, talk of secondary qualities, primary qualities. There's a long history there. But that history has to have been gone through. The student has to have learned some philosophy. That will be enormously helpful in this case.
Right.
And despite the fact that you think this is totally obvious, and it is for us obvious, it's not going to be obvious to the student who hasn't thought about it a while. And the same thing is true as, of the situations we're disagreeing about, except they're much less clear-cut.
Well, but let's see. Let's push this a little further. Somebody says to you, yeah, in that case it's the feel of heat. In your case it's the look of chairs. Okay? Somebody says to you, look, there are these features of the wave function that have all the functional relationships to other things in the world that chairs do. Suppose somebody says to you, maybe it's a misreading of you, but suppose somebody says to you, what you're doing in response to that is saying, I know all about the functional relationships. They're not chairs, okay? Why aren't they chairs? Because chairs are three-dimensional objects.
You're going to get to the marvelous point, right?
Yeah.
So we could look. You know this won't be settled here.
Well,
But I have a feeling if we continue this discussion like in Lake Placid, it won't be settled. But we're not going to get to anything else.
Okay, good. But it's a better. The heat thing is a better analogy with the mass density than it is with the marvelous point. But okay. Good. Yes. Right.
Unless you want to move on to...
No, it's okay.
Well, I can think of two other reasons one might go against your view, which aren't as laden with a priori prejudices, Shelley's and Tim's. And one would be, well, one I don't want to talk about too much, but I think that if you're already committed to some vehicles, some Bohmian particles, some GRW flashes and that, then you really should just think of the
the wave function as the Schrodinger equation is just the best system for those things, and not really think of it as an extra bit of ontological furniture.
You mean not think of the wave function as an extra bit? Right.
And so then you don't have to go, well, you could choose I guess you could choose a high dimensional viewable or not, and then why would you? But the other thing I wanted to say was, I'm not really sure it can escalate up to the point of an actual objection, but there's a sort of, maybe the smell of a possible objection where, think of in Reichenbach, where Reichenbach, so he discusses this in a classical case, where he says, look, you could go with a classical 3 space, or you could go, I think he uses mu space, and you could go into mu space. And you have exactly the same amount of information in both. You don't lose any information from going from you can map it, everything into each other. You don't lose any information at all. So why do we like 3 dimensions versus 6? And he says, which is kind of ironic in light of the subsequent thing, he says it's locality. We like locality, and we don't have locality in U space, but we've got it in 3 space.
Mm-hmm.
And then you can now see your argument in a way as sort of continuing that Reichenbachian argument and saying, well,
you mean you have locality in
now we have.
But I would say, sorry.
I don't want to get stressed out on the locality business.
Okay.
But anyway, more like the Reichenbach business, where so now you have these 2 systems. So think of the conventionalists that they can, they've got these alternative descriptions of the same phenomena. So think, you could do universal forces versus curved geometry, and often, when you look at these conventionalist alternatives, if you just narrow in on a little bit, it looks like you've got a real fight on your hands, because you could go this way, you could go that way. Yeah, so when I teach conventionalism, I'll stand there at the board and defend the hilt, as far as I can go, the flat Earth theory.
Right.
So the flat Earth, the students shout out, phenomena that's hard for me to explain.
Right.
I'll come up with some shit explanation.
Right.
And then now the resulting theory gets more and more unwieldy and more and more bullshitty. And so I'm suspecting that and the same kind of thing happens. I think if imagine tweaking the speed of light. If you think of actually tweaking the speed of light, it'll have all those ramifications that just screw up so much of the rest of the theory. And so I'm wondering whether something similar might happen here, where so you I think of the high dimensional case as the real one, but now all those other laws that were privileging the 3-dimensional, 4-dimensional symmetries, all these places where all these symmetries come up, so all of that stuff is all going to have to be reproduced by you, and so, and then will the reproduction end up becoming similarly unwieldy? I'm trying to imagine an objection that going that way.
Right.
But that's not so much a kind of, I know what the fundamental structure is, or anything like that.
Right. Yeah. Okay. I mean, let's.
Some scientific virtues.
Good. I mean, there's. If I'm supposed to give it, we already know a lot about how to read claims about what's going on in 3-dimensional space off of the wave function. That's what we've always been doing in quantum mechanics. That's what Bohr's rule is about, so on and so forth. This thing that's being referred to as this elaborate project, it's been done. That's the way we've been doing quantum mechanics from the word go. Okay. I'm not sure I see. Yeah, I'm not sure I see what's going on there. That is, it isn't as if we're faced with this weird-looking glop, okay, undulating around in this high-dimensional space, and you have to start to scratch your head and saying, how am I ever going to make a connection between this and some story that I want to tell about what's going on in an emergent 3-dimensional space? We know all about how to tell that story. Okay, that's what we've been doing forever in applying quantum mechanics. Okay, with the Bohm rule, and the things that exploit the Bohm rule, like the mass density rule or something like that. It isn't as if The deal here is that we're starting with an object that we've been using for 70 years.
So I'm thinking more along the lines of, so you're gonna have to, so you can tell a story if you pick a certain Hamiltonian.
Right.
That's gonna have to be a kind of initial condition.
The Hamiltonian? Why do you say
Some kind
that?
of constraint so that I can get out the. So I can
No, the Hamiltonian is
get
a
out
Hamiltonian. I mean,
Well, it's gonna have to, if you think of your paper where you give different Hamiltonians and there's gonna be the one.
Oh, yeah. No, different Hamiltonians would make space look differently
So
dimensional.
now I've got all these group facts now about the universe.
But wait, was the Hamiltonian of the world,
But most
is
people
the
don't know
Hamiltonian?
well, you're having, the
I'm
theory
sorry, I
that you're
should-
talking
yeah,
about.
you're
This is a
absolutely-
private debate.
Absolutely right. Absolutely right. Let's go on to Bohm's theory. Let's go on to Bohmian mechanics.
Very
Yeah.
quick thing. You mentioned something about the theory having predicting effects, ionization or temperature effects. Are these just way too small for it ever to have any prospects of actually?
No, not ever. No, like I say, the ionization effects, okay, there is, so let me give you a little piece of information. On the original version of the GRW theory, the collapses happened, the rate of collapses was uniform over all kinds of degrees of freedom, okay? That is, it happened at a certain fixed rate per particle, completely independent of what kind of particle it was, okay? From the beginning, people said, gee, maybe that's not the most natural way to put it. Maybe the rate of collapse ought to be proportional to mass or to some other feature of what kinds of particles these are. But in the original theory, it was absolutely uniform, okay? It made no difference what kind of particle it is or anything. As far as I understand, Philip Pearl, by analyzing this data from these proton decay experiments, has already shown that the ionization rate that would result from that theory for electrons is too high to be consistent with the data from those experiments. So my understanding is that that original version of GRW has already been experimentally ruled out by these ionization experiments. So no, it's absolutely not the case that the effects are so small as to never be imaginably observable. Okay. It's also the case, as far as I understand the matter, that it's thought that these kinds of collapses might slightly raise the resistance of certain superconductors because those superconductors, the zero resistance of those superconductors depends very sensitively on highly correlated collective quantum states among a lot of particles. I understand there are people who are looking for those kinds of effects. So no, it's not at all. It's not at all, sort of hopelessly beyond the range of experimental investigation. There's a very nice paper sort of summarizing the degree to which existing experimental results constrain something like, families of GRW theories by Robert Tomulka. Do you remember the name of that paper, Shelley?
No, but is Allison here?
Yeah, I'm down there. I've got it on my computer. It's like a 2011 version. It has it. By the way, the last time it was flat as well, which showed you the product.
What's that?
Before we were talking about whether you could measure one of the parameters independently of the other one.
Yeah.
There are some fraction experiments which prove that.
Good.
So most of the experimental results are kind of curved.
Right.
There are some horizontal ones.
Oh, good. Thank you. Yeah.
Following up on Frank's point a little bit, so if you have two isomorphic mathematically dual theories, it's not easy to decide which one has the objects in which theory has the better ontological status, especially when they look very different from each other. For example, like in the ADS-CFT correspondence, you have this sort of holographic screen, a two-dimensional screen, outside our space. That seems like not something that we want to accept the ontological reality of.
But wait, I'm not sure how that applies to this discussion. That is that the pure wave function version of GRW and the mass density version of GRW aren't isomorphic in any sense. They have different numbers of objects in them and different kinds of objects in them. They're not isomorphic.
But it's still true. These things are related.
So say more.
No, actually, I'd like, good if we just,
Like to get onto Bohm.
because we're not
Okay.
getting anywhere.
Okay.
What is it that you were saying about the ideas CFT correspondence? I don't know if that applies to here. You have two signs which are theories which are physically equivalent and with different mathematical structure, as you said, but these mathematical structures are isomorphic.
Right.
So I'm not sure if it applies.
I'm not sure it applies here either, but Chris, you wanted to say something?
Sorry, I know you want to move on, but I mean, there really are some interesting philosophical implications of the view that's been proposed and that's being debated, and, you know, a lot of it sort of rests on how one understands this term emergence that keeps coming up, right? And so, first I just want to ask to get clarification, you know, what sort of relation is standing behind this term? Are you just thinking supervenience of some kind?
No.
Is this
No.
functional analysis?
Yeah, it's more like functional.
So,
now.
right, so insofar as there's a functional analysis kind of thing going on,
Right.
there's going to be obtaining metaphysical realization relations, right?
Mhm.
And the literature on that is really interesting insofar as there's an express interest in what precise relata get into that relation, right? So you have some people who think that the fundamental base is going to be, they're going to be physical tokens, concrete tokens, and then realizing the emergent bit is just going to consist of properties. And then you have other folks who say, no, look, the relata of the metaphysical realization relations are going to be property instances. Anyways, the debate is really interesting, and they really, really focus on what the precise relata are. Now, here's, I think, an interesting implication. It looks as if you're going to end up, David, and correct me if I'm wrong, with, you know, a scientific manifest image that consists of
Right, those are usually opposite things, the scientific image and the manifest image.
Sorry, the manifest image.
Yeah.
Not the scientific image, right?
Yeah.
Because that would be the fundamental part. The manifest image is going to consist of properties, or property instances, or, you know, whatever, you know,
I don't think so.
these folks suggest are the proper relata.
No, I think it's going to consist of objects. But
Then they can't stand in metaphysical realization relations, in which case functional analysis is even going to work.
well, I don't know. You're getting over my head here.
So the idea is just this.
I probably don't know enough about this to give you a good answer.
The idea is just this.
Yeah.
There's a literature on
Yeah.
the metaphysics of realization.
Right.
Functional analysis is going to incorporate metaphysical realization extensively and essentially. And if you look at the literature on metaphysical realization, there's this intense focus on what the proper relata are.
Right.
And it's a weird implication that in the manifest image, not scientific image, you've got solely properties or solely property instances or weird kinds of states and affairs. That's strange. I'll put the point to Barry, and Barry seemed to agree that that's a weird sort of like...
Very sick.
Anyways.
Yeah, good. I don't know. No, it sounds like there are very real concerns there, and I should probably think about it. I have to learn more about what's at stake there. Let's talk about Bohm's theories. So, Bohm's theory, you have a completely different approach from the word go. That is, you're not going to try to solve the measurement problem. You're not going to try to put familiar objects in determinate spatial positions by altering the dynamics of the wave function. You're going to keep the dynamics of the wave function exactly what it always was, the linear deterministic Schrodinger equation. What you're going to do, rather, is enrich the ontology. Okay. You're going to say, at least at a naive level, now we're going to want to have a more sophisticated discussion of the appropriate way to think about this metaphysically, but just in terms of its mathematical form, okay? Instead of a wave function evolving in this 3n-dimensional configuration space, what you have is a wave function in what Shelby likes to call a marvelous point, okay? Evolving in this 3n-dimensional configuration space. The marvelous point moves along with the currents in the wave function, with the probability, with what we used to call the probability currents in the wave function, at the point where that particle, where that point happens to be located. Okay. So in particular, the velocity of the marvelous point is always equal to the probability current at the, now this is a 3n-dimensional x, okay? At the location in the high-dimensional space where the point happens to be located, divided by the probability density there, okay? That gets you a velocity, okay? As a function of the location of that point. And very crudely, the idea is something like this. First of all, let's start off like we did in GRW theory with the single particle theory. Okay, so the high-dimensional space is just a three-dimensional space. Okay, and the marvelous point is just the location of the marvelous point is just to be understood as the location of an ordinary three-dimensional particle. Okay. We have a theorem. This is called the guidance condition. So there are two equations of motion. And there are two dynamical equations in Bohmian mechanics. There's the Schrodinger equation, which governs the evolution of the wave function. There's the Bohmian guidance condition, okay, which governs the evolution of the marvelous point. Needless to say, both the probability current and the probability density are obtainable from the wave function itself. Okay, so what you do is first solve for the evolution of the wave function, pick some initial location for the marvelous point. Once you have that initial location, you use the values of the wave function around that location to calculate the probability current and the probability density there. That specifies a velocity for the marvelous point at every time, and the marvelous point will get carried along deterministically depending on its initial position.
But David, do you think it's a good idea to first present Bohm in terms of the marvelous point?
No. I emphasize that this is just a mathematical presentation.
I know, but
I'm not sure mathematically how to present it if I start out with multiple particles in three-dimensional space.
by saying you've got multiple particles in three-dimensional space. And write down equations for
I'm
them.
happy to say that. Good.
I mean, the marvelous point is a funny locution, which is very...
Good. I really wasn't trying to prejudice the conversation in that way. I was just trying to present it in a mathematically simple way. Good. Let it be the case, which is, I guess, the standard interpretation, that what we're talking about is n particles in a three-dimensional space. Okay. You can represent those particles, the positions of those particles mathematically by a point in a 3n-dimensional configuration space. Okay. You can represent the wave function in this 3n-dimensional configuration space, and you can associate a three-dimensional velocity with each of those n particles. Okay. By calculating a 3n-dimensional velocity of this point that represents their configuration in configuration space by means of a formula like this. Okay. And we have a simple theorem to the effect that if the evolution of the Schrodinger equation is governed, if the evolution of the wave function is governed by the Schrodinger equation, and the evolutions of, and the velocities of all the particles are determined by this, okay? Then, for example, in the one particle case, if you start out with a certain probability density, okay, over initial positions of the particles that's proportional to psi squared. Okay. If it's initially proportional to psi squared, you evolve each of those things forward in accord with the Schrodinger equation and the guidance condition. That relation between, say, the density of hypothetical positions here and the wave function is going to be preserved for all future time. Everybody with me? Shelley, you're more than invited to add stuff here, if you'd like to. Good. What this means, okay, is that the probability of finding the world in a certain configuration, in a certain three-dimensional configuration of particles, at any time in its history, is going to be exactly the, I shouldn't have said finding, the probability of the configuration of the n particles in the world being this or that, okay, at any time in the world's history, okay, is always going to be the one stipulated, but the one you would get from the Bohm rule, okay, if the wave function were always evolving in accord with Schrodinger's equation. Okay, so for example,
So let me jump in then.
Please.
There are two ways to understand, there are two versions of that statement. And one's version one, and this is good when you're first learning Bohmian mechanics. You think about probability in a naive way, and you just don't understand it in a naive way. And then, of course, when you think further, you wonder, what the hell did I mean by that?
Mm-hmm.
But you shouldn't worry about that when you're first learning.
Right.
Actually, it's really far down the line when you're dealing with any good physical theory that you should start worrying about the meaning.
I take it that a useful naive way of thinking of it is just, God started the world by picking a wave function and then choosing.
No, I mean, I'm not even, usually you don't worry with this first naive exposure.
Okay.
You feel pretty comfortable in that probability. It's only when you start to think about it where you wonder, what the hell did that mean?
Right.
Don't worry. Second way of thinking about it, purely mathematical statement. If you put on this object called the probability distribution and evolve it, it evolves in that way.
Right.
Now that is a statement nobody should have any trouble with because it's a purely mathematical statement.
Absolutely.
And you might think it's going to have an important role in making contact with the more intuitive kinds of statements and uses of probability that you want the theory to come to grips with.
Good. Sounds right to me. Good. The tables and chairs and measuring instruments and billiard balls and people and buildings and so on of our everyday experience of the world are going to be identified here with configurations of particles as they are in classical mechanics or something like that. Okay? Good. So, needless to say, by construction, there's always going to be a determinate factor in matter. And here, as opposed to in the GRW theory, that's not going to be approximately true, that's not going to be usually true, and that's not going to be macroscopically true. It's going to be microscopically true at all times, under all circumstances. Okay?
By the way, though, in GRW theory with mass density, there's no question the same thing is true.
Well, except that the mass density gets spread out. The mass density.
It's determinate, whatever.
No,
it
the
is.
mass density is determinate.
So whatever is playing the role of the particle,
Yes,
they're exactly parallel in terms of this
I'm not sure I agree
respect.
with that. But I mean,
Because you don't like the mass density.
it's absolutely right that there's always a perfectly determinate fact about the mass density at every point in space. That's right in GRW.
And the mass density is parallel to the particles, according to many people's views, namely the people who are working on sheet.
Good. Anyway, here, the particles always have microscopically exact position. This, like I said, the tables and chairs and billiard balls and people and buildings of our everyday empirical experience of the world are one needs to, modify this a little bit later on down the road, but to a first approximation are identified with these configurations of particles. The measurement problem is transparently solved. The probabilities of these configurations are transparently the Bohm rule ones. That's an extremely brief thumbnail sketch of the technique for solving the measurement problem in Bohmian mechanics. This is a completely deterministic theory that, unlike GRW, that is the dynamics are completely deterministic. The only point at which anything probabilistic enters the picture is, like in statistical mechanics, in terms of something like the probability distribution over initial conditions, here over initial positions of the particle, given the wave function. There's at this point a huge number of different directions one could go in terms of discussing the theory more deeply. But that's very crudely speaking how the theory works.
There's one thing I would add on this level of presentation to connect up with your talk this morning.
Right.
Talk
loosely.
Another thing that you get, and this is a bit paradoxical from Bohmian mechanics, is that it turns out as a theorem of Bohmian mechanics that in measurement situations, the wave function of the system collapses exactly according to the usual textbook rules, stochastically and so on. I say it's paradoxical because one of the fundamental equations of Bohmian mechanics is the usual Schrodinger equation. It's not like GRW, that's totally deterministic. Thus, there seems to be a conflict in the two statements, but nonetheless, they're both true.
Well, one can say it a little less mysteriously.
One could give details,
there's the only part of the totality of the wave function, because the wave function of base Schrodinger's equation is always there. But with each measurement event, there's a new restriction on which parts of the wave function are going to continue to be relevant to the motion of the particle.
But a more precise statement is that you can define a wave function of a system in a precise and sharp way which completely agrees with whatever anybody ever means by the wave function. And that behaves exactly
like a collapsing wave. Yes, I agree. Yeah.
It's slight caveat. I mean, you're going to need dynamical background assumptions so that the other bits of the wave function don't later come and interfere with the relation.
Well, later things could get messed up, but decoherence is going to play a role.
Decoherence plays a role.
Decoherence definitely plays a role.
Here's something maybe important to say about all approaches to the wave. Okay, all approaches to solving the measurement problem. I don't know of any approach, any promising approach to solving the measurement problem in which decoherence doesn't play a crucial role. Okay, decoherence is a very, very important phenomenon in considerations of solving the wave function. The only mistake people have made about decoherence is in imagining that somehow it by itself can solve the measurement problem. But in the GRW theory, decoherence is crucial for making it clear why empirical differences between something like a collapse theory and something like a non-collapse theory are going to be very difficult to detect. Similarly here, okay, empirical differences between a theory, the reason Bohm's theory and GRW theory, which make very, very different claims about how the wave function evolves, are both good candidates for explaining all the experimental data we have right now, has to do with decoherence. Okay? Decoherence plays a very crucial role in understanding how any existing solution to the measurement problem works. All that's crazy is the thought that decoherence in and of itself somehow constitutes a solution to the measurement.
And while a lot has been written about decoherence in recent decades, the best kind of early description and detailed description of decoherence that I've seen were in Bohm's original papers.
Really? When was sort of like
50,
Denieri?
52. No, in 52.
No, but when were Denieri and those
Those
guys?
were the late 50s, early 60s.
That's interesting. And nobody said anything about it before that? Before the
I bet you they did, but I happen just to have seen it in Bohm.
Maybe another comment. Both Bohmian mechanics and GRW are radically non-local theories. We know they must be, okay? Bell's theorem tells us that any theory for which there's a fact of the matter about how the measurements came out, and there are such facts, that the whole point of both of these theories is to ensure that there are such determinate facts of the matter, are going to be Bell's theorem tells us to expect that any such theory is going to be non-local. These theories are non-local in different ways, but both of them exactly in accord with what Bell told us to expect. The GRW theory, the collapse in the GRW theory is a radically non-local event, as I think somebody mentioned before lunch. It's something, the multiplication of the wave function by this Gaussian is something that affects the wave function throughout all space. In Bohmian mechanics, the non-locality comes up like this. As a general matter, if you move one, if you have some collection of particles and you move one of them, okay, that changes the location of the marvelous point associated with the configuration of the particles. That changes the location of that point in the high dimensional space. It moves it to another place where the currents in all of the three end directions might potentially be different than they were at the original location. Okay, so as it were, imagining a counterfactual in which one of the particles is in a different position might lead to different counterfactual velocities for all of the particles. Okay, it's essentially from that kind of geometrical structure that non-locality enters into Bohm. Bohm...
Maybe, JB, let me add something, or just say what you said in a simple way. Maybe it's a simple way. According to the velocity formula, the guidance formula,
right,
written out, if you were to write it out a little more explicitly, the velocity of particle I, or one of the particles, explicitly depends on the position of particle J. That's right. What you would just say.
Right. That's exactly right. There is this difference. Looked at, you may want to consider this abstractly or you may want to consider it physically, looked at anyway mathematically in a high dimensional space, Bohm's theory is completely local. Okay? That is, the particle, the marvelous point is just affected by the current and by the currents exactly at that point in the high dimensional space where it happens to be sitting. GRW, on the other hand, is non-local even in the high dimensional space. Or another way to put it is, if you look at the version of GRW just for one particle, okay? If you look at Bohm just for one particle, the particle is going to be pushed around by the wave function where it is, okay? If you look at GRW just for one particle, the collapse is still going to be a non-local event, even in the one particle case. So they're non-local in quite different ways. You can look at the non-locality in Bohm as a sort of projection down onto the three-dimensional level of a local dynamics in a higher dimensional space. It won't be possible to think of GRW that way. GRW is maybe, so there are some ways of describing it in which it makes sense to say, but like the way I just did, in which it makes sense to say GRW is more radically non-local than Bohm. There are other ways of describing it in which the non-locality in Bohm is much more vivid than the non-locality in GRW. In Bohm, well, I won't go into the details about that now. Yeah.
So I don't know if we want to. I just had some sociology kinds of questions. I was sort of reared in this stuff at Rutgers, so I'm very familiar with sort of like Bohm interpretation and the GRW stuff. But Bohmian mechanics is somewhat unpopular, right, in physics departments, and I was just curious.
So is GRW, I think.
Yeah, so I'm just curious, like, maybe for others that might
Right.
come out of other places,
Right.
you know, why is it so unpopular, and you know, what are some of the alternatives, and how do they, that was a big question.
I mean, yeah, you know, and Shelley ought to have a lot to say about this too.
Well, you know, you can just imagine, you know, with standard textbook quantum theory, you have wonderful notions like complementarity. They all go away. I'm just kidding. I mean, it's a lot of history.
I mean, really a lot.
I didn't like it when I first learned it because well, the basic reason I didn't like it was because it conflicted with so much that I had been taught about quantum mechanics. And I took that seriously because I thought my teachers knew what they were talking about. But actually I was wrong.
Isn't one of the objections?
Someday you'll be thinking back on today with the same thoughts.
Isn't one of the objections to Bohmian mechanics that it changes the Schrodinger equation now by?
No, Bohmian mechanics doesn't change the Schrodinger equation. GRW changes the Schrodinger equation.
I think the main judgment is that it violates relativity.
So once again, there's a long story about the relationship between Bohmian mechanics and relativity, and like Shelley was saying, there are several different ways in which you might take that question. First thing to get out of the way, vis-a-vis sort of vis-a-vis, you know, the observable features of the world that lead us to believe in relativity. Okay, there's no problem reconciling Bohmian mechanics with those.
You still can't signal faster than light.
What's that?
You still can't do faster than light signaling.
No, you can't do faster than light signaling. And we have, you know, we've had, you know, since when was Bell's paper on vehicles for quantum field theory?
83, I think, but I'm not sure.
Yeah, we've had for at least 30 years now a version of Bohmian mechanics for relativistic quantum field theory that trivially reproduces the same experimental probabilities, the same observational probabilities as as ordinarily interpreted quantum field theory. Now, it's a feature of theories like that there's a deeper sense in which they fail to be Lorentz invariant. There's a deeper sense in which they fail to be relativistic. They all make use of a preferred frame of reference, okay? It's a theorem in all these theories that the identity of the preferred frame is undiscoverable by any, even in principle, possible experiment, okay? But these theories all do make use of a preferred frame in order to write the theories down, okay? So there's a deeper sense in which they fail to be Lorentz invariant. Now, there are two questions about addressing that deeper issue of Lorentz invariance. Question one, is it obvious that you even need to, okay? Question two, if it is thought that you need to, there's a lot of work by people like Shelley in coming up with versions of Bohmian mechanics that are Lorentz invariant in a deeper sense than that. Crudely speaking, the kinds of strategies that people try to follow, or among the kinds of strategies that people try to follow, involve not picking out a preferred foliation of space-time in order to set the theory up, but using the actual, evolving wave function to pick out moment by moment the preferred foliation of space-time, which you can then feed back into the theory. So there are all kinds of senses of Lorentz invariance. The sort of observational sense of Lorentz invariance is trivially satisfied by Bohmian mechanics. What you might call a deeper, more metaphysical sense, or rather, one can think of several deeper, more metaphysical senses of Lorentz invariance. Some of those we may be able to formulate versions of Bohmian mechanics that satisfy them. Others maybe we can't. That's where that's.
Let me make a suggestion, a terminological suggestion
Sure.
here. I think the notion of being Lorentz invariant, even though there's a question of distinguishing serious Lorentz invariance from non-serious, it's still a much clearer notion because it's mathematical. When you think about it, the notion of being relativistic is much less clear. So I would say the real question is going to be, at the end of the day, is the theory you come up with genuinely relativistic? And to get an appreciation of how this could be difficult, tricky, well, one thing you might demand of a relativistic theory, and people did, is that it be local. Well, if you're going to demand that, you're not going to succeed. At least not in anything but possibly an Everettian framework.
Right.
So, what?
Anyway, I'm sorry, I didn't mean to interrupt.
That's all I really. So I mean, so that I think that's an important question. What exactly does it mean for a theory to be relativistic?
Right.
Can you think of this preferred term as a local hidden variable or a non-local hidden variable?
I don't know why it would be. I don't know why. First of all, the whole term hidden variable is an unfortunate historical
description that you don't have access.
Let me answer the question though. There have been various proposals for introducing a frame in a Lorentz invariant kind of way. In some of the proposals, the frame was introduced as an additional piece of structure. So that's a hidden variable, something beyond the wave function. And as David said, it's also hidden. Now, in the proposal David referred to before, the most recent thing, the frame is determined by the wave function, so it's not a hidden variable.
Right. Yeah, David.
I mean, just picking up more on Chris's question from somewhat more critical perspective here. I mean, two things I think are relevant to where this goes. So the first thing I think is that I think the issue of extending these things beyond quantum mechanics remains kind of complicated controversial. And Ward story here knows much more about it than I do. But we have Bell's strategy, which looks good as a route, and Ward and Samuel Cohen, I think, developed more sophisticated versions of that. But raised some concerns and things need to be filled in. There are versions which take particles as a basis, which Shelley and Derby will develop. There's another version of Ward and Hans Westman developed, which is close to ideas has to be guaranteed. There's lots of routes here. It's not clear that these things have been fully run through all of the various bells and whistles and cogs and gears of
Definitely not, that's for sure.
So there's still questions in the air there.
Mm-hmm.
The other thing I think is not entirely separate, and you can call this semi-sociological, if you ask why in physics context does this not used very much. I'm sure some of the answers things that Shelley brings up, but this is a pragmatic reason, of course. The calculational results you get, by design, the predictive calculational results you get out of the theory are the same as the results you get out of quantum mechanics. And to get them out of the theory, you have to run the quantum mechanics first. You have to solve the normal quantum mechanical rules. After that, you need to. I mean, there are some examples where.
Well, wait. Of course, say with GRW, the calculational results aren't exactly the same.
No, I'm talking about Bohm, sorry.
Oh, okay.
Yeah.
Let me make a, but and here's something I don't understand very well, but it's nonetheless a fact. It turns out that a lot of quantum chemists are using Bohmian trajectories to solve Schrodinger's equation. Now, what you just said would make that surprising, and I am surprised. That's why I say I don't really understand it, but it is a fact.
Yeah, that's why I wanted to edge it a little bit. It's not.
Yeah.
I mean, it's not the mathematical. I mean, here's a guess. If the mathematical technology of Bohm mechanics had turned out to be ubiquitously and wildly helpful right across the face of physics, I think we'd be seeing a different situation.
Yeah.
With the exception of that last thing to turn out.
But look, there's a deeper story. And I mean, this is a story, frankly, which, I think there's an enormous story of the intellectual history of the 20th century to tell here that has never even remotely been well told or attempted to be told comprehensively, and it would be a large and challenging intellectual project to tell such a story, it seems to me. But there is independent of what people think of Bohmian mechanics and so on and so forth, how it is that people manage to psychologically insulate themselves from the measurement problem for so many years and how it is that for about half that number of years, but that's still an enormous amount, they managed to psychologically insulate themselves from the consequences of Bell's theorem and so on and so forth. This is a really bizarre story, okay? This is, I mean, you have at the same time the following two wildly contradictory things going on. The 20th century, it goes without saying, wildly outstripped every other century for the rate of scientific progress, for the number of smart people who were interested in physics and working actively on physics, so on and so forth. That same century witnessed the longest period of kind of psychotic denial, you know, of this deep logical problem right at the center of this whole project. This is a really interesting story. I'm convinced that there are, you know, deep cultural components to this story, political components to this story, economic components to this story. This is a really rich, interesting, deep historical story. I think there's a hell of a lot to say about this. There's never been even much of an attempt, as far as I know, to tell this story in an interesting way. And I think a proper telling of this story might shift lots of our opinions about the intellectual and cultural history of the 20th century. I think there's a really, really interesting story to tell. But it's a big project to tell such a story. Good.
Let me add something to what David said. I guess it's particularly appropriate at the summer school in philosophy of cosmology to say that the way one wants to think in terms of cosmology, the Bohmian point of view would be kind of helpful because there's no outside observer. If you're doing ordinary physics, you're always doing experiments, and some observers ran around it. But if you're thinking about cosmology, a Bohmian perspective is very helpful.
I mean, it's also, I mean, it's true that in non-relativistic quantum mechanics give the same predictions, but that doesn't mean you can't use it as a kind of heuristic when moving forward to a new theory. And so you could, it could be that it, well, it seems like there's two sorts of cases. So there's a case like the quantum chemist, the Bohmian quantum chemist that Shelley mentioned, where you're developing these new practical tools, which also Ward is doing with semi-classical quantum gravity. Or it could be something more theoretical. Both Shelley and I have written papers on Bohmian insights into quantum cosmology and the problem of time.
Right.
So there would be, when you're moving outside non-relativistic case, it could be a useful guide or fruitful, helpful.
Yeah, I mean, it certainly is the case that the one place, and this relates to the topic of this workshop, the one place where one sees within, physics itself, the one subfield of physics where you get a lot of sympathy for attempts to develop a version of quantum mechanics that doesn't require an observer standing outside the system is in the context of cosmology. For Everett, this was quite an explicit motivation.
I think it's fair to say, it's true, I think it's fair to say that most quantum cosmologists seeking an understanding of quantum mechanics and observables did not go in this direction.
Did not go which direction? I mean, Bohm.
The Bohmian direction.
The Bohmian. No. But I mean, the one subfield of sort of physics proper, it seems to me, where there was a great deal of sensitivity to the measurement problem in general, was in cosmology. Okay? And certain solutions to the measurement problem, like the Everettian proposal, were developed very explicitly because it was thought that this was going to help out.
Everett was quite upfront that he wasn't, at least in what he published, which was restricted and constrained in various ways, and he knows more about designing. The actual published paper was quite explicit that the problem it had in mind was quantum cosmology, not measurement problem per se.
Right.
The quote is something like the Copenhagen interpretation is fine for these Bohmian lab cases, but whether it was
Well, the problem with that, of course, is that published version was an edited version of the original paper, which was about the measurement problem.
Right.
But, actually, when we're talking about this at 4:45, trying to address it in a modest way with data, just ask to be done, which is to contextualize this denial. And, with Everett, it's easy enough to see why people didn't like him, because he had all this metaphysical baggage, according to Wheeler, extra universes, blah, blah, blah. But what's the problem that you think that people would have with Bohm? Aside from the fact that he...
Oh, well, there are standard complaints about Bohm. Bohm, in the earlier version, due to De Broglie, there's a famous story that Pauli said to De Broglie at one of the Solar conferences, look, according to your theory, an electron in a ground state orbital in a hydrogen atom would be stationary. Okay. And the correct answer to which was, duh, so what? Okay, it's reproducing. I take it the implication of Pauli was if it was stationary, it would fall into the nucleus. But that's of course not the case on Bohmian mechanics or on the version of it, the simpler version of it that De Broglie was presenting. And my understanding was that instead of De Broglie saying, yes, of course that's true, what's the problem with that? He sort of said, oh, I'm sorry.
No, but it was worse, David. Pauli talked about an experiment involving elastic scattering based on ideas of Fermi, and it seemed kind of puzzling how it would work out in Bohm. Well, it wasn't Bohm, in De Broglie.
Right.
And De Broglie's discovered was the first. De Broglie is the author of Bohmian mechanics. So De Broglie tried to respond, and he gave a terrible response. Just a wrong response.
Right.
And that made a pretty bad impression. And
Right.
in fact, De Broglie almost immediately abandoned his name.
Right.
And it was only later that Bohm gave a proper response
Right.
to the question of Pauli.
Right. But I take it, I take it that the particular reaction to something like Bohm or GRW was a secondary phenomenon. The primary phenomenon was an unwillingness to understand that there was a problem at all, I take it.
That was one thing. There was certainly the fact that everybody knew that Bohm didn't work because Bell had proven it.
Mm-hmm.
That was certainly something I was told
Right.
as a student
Right.
repeatedly.
Right.
If you're a good student, you listen.
Right.
What?
Maybe that's a good place to end up. Just because that's another thing that there is sort of very widespread.
Another widespread thing is this
Yeah.
common objection. You've got this crazy pilot wave in the theory. We have to add this extra pilot wave. The irony there, of course, the pilot wave, that is the wave function, was the thing you had all along. It's not the thing that got added.
Who said that?
Lots of books do.
Really?
Lots of popular books.
Well, most of them. But, Bohm wrote this great textbook, what, 1952 or something?
Yeah, but that wasn't about Bohmian.
I know, and that's the cool thing, because the last chapter is all about what we're talking about, and he came down on the side, more or less of the Copenhagen so-called interpretation, but he asked all these questions in that chapter that actually led to him formulating his theory.
I mean, here's the story I heard. I'm sure you know more about this than I do. But I think maybe I heard the story from Bohm, but I'm not sure. That he,
You don't have a more reliable source?
Bohm was, but I'm not sure that I'm reliable here. I don't know, this is some combination of mythology or stuff that I heard from Bohm or something like that. But, Bohm's reaction to the fact that he couldn't make clear sense of Copenhagen was unendurable guilt, okay? And he was suffering, and he felt inadequate, and he felt bad, and so on and so forth. And he needed to cure himself of this inability to acknowledge the truth of the Copenhagen interpretation. And decided to write the most elaborate defense of the Copenhagen interpretation that anybody had ever written, okay, which was his textbook, okay. And he finished it, and he was in Einstein's office at Princeton after finishing the book, after the book was published. and said, look, I can only tell you this, but I'm still unable to accept, Copenhagen as my savior. I'm still struggling with this. I can't do it. I can't quite get my head around it. Blah blah blah. And Einstein reportedly said to him, "Look, you're a schmuck. Okay? You've given everything anybody could give to producing a defense of Copenhagen. You've proven more clearly than anybody else could have proven that a successful defense of Copenhagen is impossible to do. Why don't you give yourself a break?" Okay. And Bohm, what I remember Bohm saying to me is that he went out of Einstein's office feeling like an enormous weight had been lifted. And within a month or two, he had his interpretation.
And then Princeton fired him for being a communist.
Yeah, that's right. No, it's quite an amazing. The story I heard about Princeton firing him is not just, he refused to testify before the Un-American Activities Committee. He was fired like that. But within the next 24 hours, there was an unprecedented emergency meeting of the trustees of Princeton University in order to pass an edict that Bohm was not allowed to set foot on the campus of Princeton University.
Oh, wow.
It was quite amazing. Yeah.
This was just organizational, and you were going to say a little bit about the other interpretation as well, it's to be useful to have as a starting point for...
Say it again.
This is just organizational, you were going to say a little bit about Everett as well.
Yeah, so let me say, okay, so good. So let's say, I also wanted, as a courtesy, to leave it, to not mess up your presentation, but let me say a bit. Good. Third, so far, two strategies have been brought into play for solving the measurement problem. Strategy one, solve the problem by sort of preserving, strategy one, hang on to the claim that the quantum mechanical wave function is a complete description of physical reality. Whether it by itself completely constitutes physical reality, let's leave that aside. But hang on to the standard idea, to the traditional quantum mechanical idea that the wave function is complete as a description of physical reality, and try to solve the measurement problem by changing the dynamical laws under which the wave function evolved. That's the strategy that culminates in our investigation so far in a theory like GRW. Second strategy, hang on to the claim that the Schrodinger equation describes the complete laws of the evolution of the wave, and let go of the claim that the wave function by itself constitutes a complete description of physical reality. Okay? That's the strategy that culminates in something like Bohm. Okay? The way you solve the measurement problem in the first case is by altering the equations of motion of the wave function, because the wave function is all you've got. The way you solve the measurement problem in the second instance is, even though you hang on to the Schrodinger equation under all circumstances, there's something else that has the kind of determinatenesses that you were looking to get in the first strategy by changing the laws of evolution of the wave. Okay, then there is this third strategy that goes back to Everett, where you want to try to do neither, okay? Where you want to have your cake and eat it too, where you want to hang on both to the claim that the wave function is a complete description of physical reality, and to the claim that in the non-relativistic case, the wave function evolves under all circumstances strictly in accord with the linear dynamical equations of motion. Yeah.
Sorry, before we go on to Everett, I have a question about Bohm. So say that you've got two identically prepared one-particle systems at different times.
Yeah.
And so then you measure their locations at a later time after you identically prepare them, and you happen to find that you get the same answer.
Yeah.
Just because you got lucky.
Right.
So these two systems have the same pilot wave in the same marvelous point up to an overall difference in time. So the equation governing the future of
Oh, why not? Oh, okay, I thought they were going to even be at the same time.
They could be, but
Right,
but
okay, yeah.
So so the equation governing the future evolution of the marvelous point is a first order differential equation, right? So
Yeah.
you're gonna, so this.
Yeah, those two things will be the same for all times.
Right, but that's not what we'd actually see, right? Because our
Oh, no, but look, once you make the measurement, okay, then you're entangling each of those systems with a measuring device. Well, let's see, there's lots of, good, but let's actually go through that. So what's going to happen in a case like that? You start off with two identical wave functions, and the particle here is in this wave function is in the same position as the particle here is in this wave function. The wave functions evolve subject to the same external influences, let's say freely or something like that. Then for sure, these two are far enough apart so that they don't interact with one another or overlap with one another or anything like that. Yeah, then these two particles are going to have exactly parallel trajectories, okay? Then we do a position measurement here. We find this one here. We do a position measurement here. We find that one there. Then we effectively collapse the wave function. So the deal is something like this. If you, of course, doing a perfectly exact position measurement is out of the question. If the position measurement has any finite accuracy, so you're going to collapse it onto a little Gaussian there, okay? Then, thereafter, the future evolution of this wave function is going to depend extremely sensitively on its exact position within that Gaussian, and similarly here, and the outcomes of those measurements are going to give you no reason to believe that those exact positions within the Gaussians were the same. And thereafter, they're going to spread out very differently. That's what's going to happen.
Okay, that's what I
Good, good. That sound right, Shelley?
I mean, you're talking about a realistic situation.
Yeah.
If you're unrealistic situation where everything was exactly the same on the two sides,
Yeah.
what you're describing wouldn't happen. But this was only for a particular kind of measurement, namely the very frequent, unusual kind, often a measurement in which randomness in the apparatus does not introduce randomness into the outcome.
Right.
In many measurements, the randomness in the apparatus is also relevant.
Sure.
So unless the apparatus states were also started identically, that's going to introduce big differences.
Sure, but that'll depart even more than this does from ideality.
Yeah, absolutely.
Right. Good. Good. Okay. Anyway, many worlds, or Everett, you want to hang on to both. Okay. You want to hang on to both the claim that the wave function is a complete description of the world, and the claim that that the wave function always and under every circumstance evolves strictly in accord with the linear dynamical equation we know. So, you want to say, in a case where I measure the x spin of a particle that's initially y spin up, the state of the world after the measurement is over is going to be 1 over root 2, indicates that up x plus 1 over root 2 indicates that down x and down x. Okay? And you want to try to figure out a way to reconcile your experience of the world with the claim that that is the way things end up, in fact, at the end of such a measurement process. There are lots of ways of getting yourself in the mood to do that. Let me tell you what my favorite ways of getting yourself in the mood to do that. What's the usual way of formulating a measurement problem? What's the usual objection to the proposal that this is in fact the way things end up? Well, the usual objection runs something like this. Look, on this way of things ending up, on the standard lore about what it means to be in a superposition, there fails to be a fact of the matter. I'm sorry, let this be believes that down and believes that up, okay? We cut out the Bohmian, we just had the guy looking directly at the spin and forming a belief, okay? Because he's got Superman eyes or something. Okay. So the usual objection is, well, I mean, how do I know this isn't what happens? Because I know, indeed, I know by direct introspection. I know with a reliability which, according to a certain Western philosophical tradition, is not approached by any other kind of knowledge that I have. Okay. I know for sure that there's a fact of the matter about which belief I have when this experiment is over, and this situation seems to be precisely denying that there's a fact of the matter about which belief I have at the end of the measure. Suppose you were to say to somebody, okay, just for fun, what would it feel like to be in this, to be the observer in this state? Okay, so this is now an observer state, and this is an electron. Okay, and the usual answer would be, how the hell do I know what it would feel like to be the observer in that state? But I don't need to know. All I need to know in order to make it clear that this isn't the state we end up with is that however the hell it would feel to be in this state, it wouldn't feel like there was a determinate fact of the matter about what I believe. And there is a determinate fact of the matter about what I believe when these experiments are over. So the game is over. This couldn't be the way things end up. Okay? Suppose the guy says, fine, just humor me. Okay? Let's play a game. I know it's irrelevant. I know it's not going to go anywhere, so on and so forth. I know this isn't the way David wants it. David is making a face to indicate that this is not the way he would want to introduce Everett. That's okay. Okay. Humor me. Let's figure out what it would feel like to be in a state like, to be the observer in a condition like that. And you say, fine, how do you want me to humor you? I mean, how are we supposed to even start to try to imagine what it would feel like to be the observer in that state? You say, I have an idea. Let's treat this observer as a physical object, okay, as we're being encouraged to by quantum mechanics. Let's imagine an interview with this observer where you regard the questions you put to him as sort of physical stimuli that he's going to physically respond to in one way or another, and you ought to be able, in principle, to predict those responses by just solving his equations of motion. Okay, let's see what he would say. Okay, you say, fine, you want to play this game? I'll be happy to play. So let's imagine several questions we could put to this observer. Question 1. Do you believe that the spin is up or that it's down? Okay. That's not going to help. If you hand him a piece of paper and allow him to write on it, the piece of paper is going to split into two branches. On this branch, it's going to have a U on it. On this branch, it's going to have a D on it. Or the other way around. No, yes. On this branch, it's going to have a D on it. That's not going to get us anywhere. Okay, we started out with a superposition of brain states. That now infects the state of the piece of paper. That doesn't give us any information. Forget about that question. Suppose we ask a slightly more devious question. Why am I saying he's going to respond to this in this way? That's part of being a competent observer. That is, if the entire state were this, he would write U on the piece of paper. If the entire state were this, he would write D on the piece of paper. And so if the entire state is in fact this, by linearity, he'll write U in this branch, D in that branch. Is this clear so far? Okay. Suppose you ask a slightly more devious question. Suppose you say, you know what, I understand that was a foolish question to ask. Let me ask the following question instead. Don't tell me which belief you have. Just answer yes or no. Is it the case that you now have a determinate belief? Or rather, yes or no, is it the case that it is now either the case that you believe up or you believe down, as opposed to anything else? So, checkbox 1, if it's the case that either you believe up or you believe down. Checkbox 2, if something else is the case, you feel nauseous, you want to go home, you don't like this game, something like that, okay? Or, box 3, if everything looks fuzzy somehow, or something like that. Good. It follows very straightforwardly. First of all, it follows from this guy being a competent observer that if he's in this state, he'll check box 1. It also follows that if he's in this state, he'll check box 1. And now it follows by linearity that if he's in a full state in the box, he'll check box 1. He'll be in an eigenstate of checking box 1. Everybody with me here? Okay. So now we've got a straight answer from this guy. Okay, deterministically. If you ask him this question, don't ask him which thing he believes. That's just going to get you sucked into the same superposition. That's not going to shed any light on anything. Okay. Ask him, is it the case that you have a determinate belief? More specifically, is it the case that either you believe up or you believe down? And nothing weird is going on, nothing fuzzy is going on, you're not nauseous, you're not upset. You just feel normal, and you either believe up or you believe down. Everybody with me? Phrase that question in as much detail as you like. He's going to check box 1. Okay? Once you see that, at the very least, you're going to tend to say to yourself, the measurement problem in its original form is not as cut and dried as it might have appeared at first. Okay? The claim that this obviously isn't the state we end up in. Okay? The claim that this obviously isn't the complete description of the state we end up in isn't quite as cut and dried as it might have appeared at first. Okay? There's more to be said. Okay? Because if this were the state you were in, and somebody said to you, does it appear to you as if a collapse has occurred, for example, which is another way of asking the same question, he's going to check yes. He's going to check yes for sure. Okay? So that if you take, now this isn't the way people will eventually do it in the many worlds interpretation, but if you were to hang on to the standard law about what it means to be in a superposition, okay, then a person in a superposition of states like this, what the equations of motion tell us is that a person in a superposition of states like this is in fact going to be radically deluded about his own occurrent mental state. Okay? That's what the equations of motion force on him. Okay? So, to pose the measurement problem by pointing out that the equations of motion by themselves lead me to this state, and it's obvious by introspection that this is not the state I end up in, okay, is a little too quick. Okay? So maybe it's worth pushing further the project of trying to imagine how it could be the case that in fact this is a veridical representation of the state we end up in at the end of a measurement event. And more than an initial, this is less of an initial description of the many worlds interpretation as sort of an invitation to it, you might say, or something like that, by way of setting the stage for what David is going to say tomorrow. Good. This was a grotesque and painful day.
You need some more universes.
But good. Well, but we're back for much more pleasant doings in 45 minutes with Peter Byrne.
Thanks,
telling
Alex.
us about it. Thanks for the fun of being able to watch someone else in pain.